Welcome back to another section, another Fourier series. So, like I said in our last video, we're going to be treating an example on how to solve Fourier series when you're not given your pi, your normal pi minus pi function interval. Sorry. So now in this case, now you're given from the interval of -1 to 1, right? So how will you go about this? So instead of me going through the steps, the stress of proving the formula, I'll just go straight to giving the formula. It's just like Fourier series, but in this case now with some lot of things that has been changed. So the Fourier series, when you're asked to solve um, function that in which they are not having intervals of minus pi to pi, the formula goes like this: fx is equal to a naught divided by 2 plus summation coming from n equal to 1 to infinity for an cos n pi x over l, put this in brackets, dx plus bn sine n pi x over l. Sorry, there's no dx because there's no integration sign, so just closing the bracket. So this is just like related to Fourier series, but in this case now you are not using just nx, you are using n pi, you are using n pi x over l, where pi x over l can be another variable z, where z is equals to pi x over l. So in this case now we introduced another variable z instead of your normal x sign, your normal x in your Fourier series question. So we introduced another variable z. So this is for the interval x from minus l to l, where l can be any value, or s can be any value, just like the one we have here, -1 to 1. So now where an is where an is 1 over l. You see, in our last video we said an, your standard Fourier series formula for al, we said is 1 over pi, right? But in this case now it's 1 over l, taking the interval, right? So this is 1 over l integral from minus l to l, function of x cos n pi x over l. So you see, a lot of things have changed. It's just like rewriting my other Fourier series formula for an, but in this case now replacing pi with l, right? So this is where an is equal to this, and bn is equals to 1 over l. It's going from minus l to l of function of x sine n pi x over l. So this is just actually a lot easier to remember. You just know that. So anyway, I see x, I put pi x over the interval I'm given. So having gotten that out of the way, so now we can solve a question. So applying this formula in front of me, so these are the formula you need to remember when you are given interval that is not your usual minus pi to pi. But if it's your not usual minus pi to pi, you use your standard Fourier series formula. So hope you note this down. So let's solve the example. Let's solve the question in front of us. So in order to solve calculate the Fourier series for this function x given in the interval -1 to 1. Now in this case now we can relate it to the interval of minus l to l, right? So in this case where l is 1, right? So l is 1. So now first thing we do is calculate an, right? So calculate an, calculate bn, and put it back into the formula. So an right here is 1, since l is 1 over 1 integral comes from -1 to 1 of function of x cos n pi x over 1, right? So let's simplify this. So this is like saying it's going from -1 to 1 of function of x cos pi x, right, of an. So your usual way, we have to integrate. So in this case now our function of x is x, right? From the formula, from the question, our function of x is x. So this is -1 to 1 x cos n, and this n pi x. So your usual way, we have to use our normal integration by parts method. So solving this, where, so if you can remember your sequential process, this is my arithmetic and this is my trigonometric. So arithmetic, I denote it x, and trigonometric, I call it x cos n by x. So arithmetic comes before trigonometric, so my x takes my u. So u is equal to x, and my dv is equals to cos n by x, right? So applying your normal integration by part formula, which says u dv is equals to uv minus v du, right? So my u right now, so let's differentiate my u. My u, that's du dx, right? If I differentiate u equal to x, I have du dx only. And integrating the v, I have v is equal to sine nx, sine n pi x over n pi, right? So having gotten that out of the way, so now let's put it back in our integration by part formula, which says u, my u is x, my v is sine n pi x over n pi, minus integral, my v is sine n pi x over n pi, then you know my du is what? Just dx, right? So taking the constant to the back of the integral sign, the constant here is 1 over n pi. So you have 1 over n pi integral sine n pi x dx. This is x sine n pi x over n pi. So let's go on. So now we are going to integrate this. This is just a simple integration for us. So integrating sine n pi x, we'll be having 1 over n pi minus cos n pi x over n pi. So this is x sine n pi x over n pi, right? So multiply through by minus sign, so this is x sine n pi x over n pi plus cos n pi x over n square pi square. So remember, all this was from integrating x cos nx, right? So what we do here is to apply my limit. My limit says from minus 1 to 1, right? So apply my limit from minus 1 to 1, right? So putting 1 here, right? So this is just like saying sine pi. So putting 1 here, this is just like saying sine n pi. Remember, sine of pi, despite the value of n here, gives me 0, and this gives me 0. So putting 1 here, this is just like cos n pi. So cos n pi will give me 1, will give me minus 1. So because n pi, the value of cos n pi depends on the value of n here, right? So we just need to write it out. So this is cos n pi divided by n square pi square, right? Minus, so we do for minus 1. So putting minus 1 here also, this is the same thing as minus sine minus n pi. And remember, despite the value of your minus 1 changing, this also gives me 0. Putting minus 1 here, so this is cos n pi minus 1 divided by pi square n square. So this gives me cos n pi minus 1 divided by n square pi square, right? So now let's continue, right? So now if you look at this, so writing this out, we have cos n pi over pi square n square, right? Minus cos minus n pi, right, over n square pi square. Now there's a rule that says cos x is equal to cos minus x. Remember, cos is an even function, so the rule for even function also applies to your cosine, right? Cos x is the same thing as cos minus x. So this is cos n pi. So cos n pi, so cos minus n pi is still the same thing as cos n pi. So replacing this with this, so this is cos n pi over n square pi square minus cos n pi over n square pi square. So this gives me 0. So we can conclude, remember, all this was from a n, right? My a subscript n is equal to 0, right? So my a subscript n is equal to 0. So don't worry. Oh, we might be asking, why didn't you calculate for a not first? Don't worry, it was just a sequential error, so we just calculate for a naught now. So in order to calculate for my a naught, right, you know, from my an, an is given as 1 over L. It's calculated from minus L to L, fx cos n pi x over L, right, dx. So to calculate a naught, now let's calculate, the formula for a naught, right? A naught is where n is equal to 0. So this is a naught is equal to 1 over L, it's calculated from minus L to L of function of x. Now when I put n equal to 0 here, which makes this whole thing here 0. So we will be having cos 0, and cos 0 is 1. So this is 1 times dx, which is dx. So this is the formula for my a naught. So which is just like the formula for a naught for your normal Fourier series interval from minus pi to pi. So where L is equal to 1, right? So this is 1 over 1. integral comes from minus 1 to 1 of function of x dx, right? Remember, my function of x from the question is x. So this is integral comes from minus 1 to 1 x dx, right? So integrating this right now, so integrating this for applying my limit, so this is 2x squared divided by 2, applying my limit from minus 1 to 1, right? So putting 1 here, this is 1 over 2. I'm putting minus 1, so this is putting minus 1 here, that's minus 1 raised to power 2 over 2. So I'm left with 1 divided by 2 minus 1 over divided by 2, which gives me 0. So if you look at this, we've gotten a naught to be equal to 0, and we've gotten an to be equal to 0 and a naught to be equal to 0. So what is this trying to tell you? This is trying to tell you that, oh, this function was assumed to be an odd function. Remember, normally your x is a function of x is an odd function, right? So so we have proved in here that a naught is equal to 0 and an is equal to 0. So this means the function we are working with is an odd function, right? So now definitely my bn, let's calculate for bn. My bn will not be equal to 0. So let's calculate for bn. So let's calculate for bn. So remember, your formula says bn is equal to 1 over L, integral comes from minus L to L of function of x sine n pi x over L, right? dx. Remember, when L is equal to 1, right? So we're left with 1 integral minus 1 to 1. And your function of x is x, right? So this is x sine n pi x over 1, right? So this is dx. So we do the normal way. Integrating this, so your normal integration by parts. So my u is x and my dv is sine n pi x. So differentiating my u, that's du is equal to dx, and integrating the v is equal to minus cos n pi x over n pi. So putting it in my integration by part formula, which says u dv is equal to uv minus v du. So my u is x, right? And my v is what? Times minus cos n pi x over n pi minus integral. My v is what? Minus cos n pi x over n pi, and my du is what? Dx. So I'm left with minus x cos n pi x over n pi plus integral cos n pi x over n pi dx. So taking the constant at the back of the integral sign, so this is minus x cos n pi x over n pi plus 1 over n pi integral cos n pi x dx. So we integrate this. This is just like a standard, a simple integration. Integrating this, we'll be having 1 over n pi sine n pi x over n pi. So this is minus x cos n pi x over n pi. So multiplying these two together, so I'm left with minus x cos n pi x over n pi plus sine n pi x over n square pi square. So remember, all this was from integrating x sine n pi x. So we apply our limit from minus 1 to 1. Apply my limit from minus 1 to 1. So putting 1 here, right? Putting 1 here, that's replacing x with 1. So this is cos n pi. Putting here 1, this is minus 1. So I'm left with minus cos n pi over n pi, right? Putting 1 here, this is sine n pi, right? And remember, sine of pi is always what? 0, despite the value of n here is always 0. So putting minus 1 here, that's 1 cos n pi. Putting minus 1 here, that's minus 1 divided by n pi. Remember, putting minus 1 here still gives me what? 0. So I'm left with just this. So, right? So we evaluate. So we're evaluating now. Remember, there's a rule that says cos x is equal to cos minus x, right? This is a rule for even function, right? Cos is an even function. So this is a rule for even function. So which means cos minus n pi is still the same thing as cos n pi. So we're putting it here. So this is minus cos n pi divided by n pi minus, this is cos n pi minus 1. That's the same thing as cos minus n pi. So which is the same thing as cos n pi divided by n pi. So these are equal. So this gives me minus 2. Let's write it out here. So this gives me minus 2 cos n pi over n pi. Whew. So you see, we didn't actually get value of 0 for bn, so I can call this my bn is equal to this, right? So now let's assume, let's check a common, let's check the way to represent it on our Fourier series formula. So now let's just substitute it back to our Fourier series formula. So since we have gotten our parameters, let's substitute to our Fourier series formula. So we had bn to be equal to minus 2 cos n pi x over n pi, or pi n, and we had an to be equal to 0, right? And we also had b cos a naught to be equal to 0. So we had a naught to be equal to 0. So these are my parameters. So we put it back to the Fourier series formula. Remember, Fourier series formula says fx is equal to a naught divided by 2 plus summation n equal to 1 to infinity, right, of an cos n pi x. Remember, it's supposed to be over L, right? But L is equal to 1 plus bn sine n pi x, closing the bracket, right? So we substitute now, since a naught is equal to 0 and an is equal to 0, so this becomes 0, this becomes 0, right? So we're only left with fx summation n equal to 1 to infinity of bn sine n pi x, right, divided by 1. Or you can just leave it like that. So you see that this is actually like the Fourier series for standard Fourier series formula we got for odd function, right? For minus pi to pi. But in this case now, this is from minus 1. It's from when x equals to minus 1 to 1. Oh, we put the value of b into our series to get our answer. So now let's look at the function bn minus 2 cos n pi x over pi n. Now this is where it gets tricky sometimes. Some people don't know how to evaluate this. So now let's assume when n equal to 1. This is just simply putting when n equal to 1, right? So when n equal to 1 in this sorry, there's no x, just n pi, right? Because we didn't get x from our we didn't get x, it was just minus cos n pi. So this is the value of b minus cos n pi. So now let's evaluate it. So when n equal to 1 here, when n equal to 1, so this is cos pi, and cos pi is minus 1. So I'll be having minus 2 over pi n times minus 1, which is 2 over pi n, right? That's when n equal to 1. So when n equal to 2, let's check when n equal to 2. I have when n equal to 2, this is 2 times pi, and 2 times pi is, that's 360, and cos 360 is 1. So when n equal to 2, this is when n equal to 1. So when n equal to bn is equal to minus 2 times 1 over pi n, which is equal to minus 2 over pi n. So if you keep on checking and checking, you see that values of n equal to 1, 3, 5, and so on and so forth gives me bn is equal to 2 over pi n. While values of 2, 4, 6, 8 give me bn is equal to minus 2 over pi n. So you see, I have a positive value for odd values, and I have a positive value of negative value of bn for even values. So now let's put it in our Fourier series question. So fx now is equal to, when n equal to 1 for bn, when n equal to 1, I'll be having this, right? So this is 2 over pi n sine nx, sine n pi x, and remember n is 1, right? So this is 1, plus when n equal to 2, remember I'll be having a negative function of bn, so this is minus 2 over pi n sine 2x, plus when n equal to 3, I'll be having positive value of 2n, right? So this 2 pi n sine 3x. When n equal to 4, remember I'll be having negative value, so this is minus 2 pi n sine, sorry for that, so this is minus 2 pi n sine 4x, blah blah blah, and it goes on and on. So I can factor out 2. Okay, remember we are missing something here. This is when n equal to 1, right? When n equal to 1, remember we need to put 1 here, so this is 1. Remember this is when n equal to 2, so this is 2. This is when n equal to 3, so n is 3. N equal to 4, so n is 4. And that is that. So factoring out 2 over pi, so this is 2 over pi, open bracket, sine pi x, plus, sorry, this is minus 1 over 2 sine 2x. Remember, when you factor out 2 pi from here, you only left is 1 over 2. And plus 1 over 3 sine 3x minus 1 over 4 sine 4x. So this is the expansion for Fourier series of x. So x is equal to this expansion. So thank you guys for watching this video. So our next video we dive into Fourier transform and so on, or we dive into Fourier integrals. So thank you guys for watching, and please do so well to hit the subscribe button, and please subscribe. It's just a 1 second process. Just hit the subscribe button, and thank you for watching. Peace.